Okay, welcome back, everybody. Yesterday, last lecture, we ended with a discussion of an Eulerian graph, and basically we covered the definition of an Eulerian graph, gave a few examples, and for the question of what sorts of restrictions uh, this places on a graph when you say that a graph's Eulerian, which means it contains an Eulerian circuit. And there was this theorem, and its corollary, which was related, which like I said you'll prove in a future homework. Basically, we saw that this is very restrictive in the sense that if you have an Eulerian graph, the only way this can happen is if every vertex has even degree. Um, so having even degree of every single vertex was required to be Eulerian, which is a pretty massive restriction on just a generic graph. This also meant, this is maybe the easiest thing to wrap your mind around. This one meant that the edges can be partitioned into edge disjoint cycles. So we saw an example of that. Here, this is an Eulerian graph. You can notice that every degree of every vertex is either 2 or 4, so it's all even. To see the edge disjoint cycles we saw yesterday, so one of them is this one, this figure 8. That's one of the cycles. The other cycle is this square. You'll notice none of those have, neither of those cycles have an edge in common, so they are edge disjoint in the sense, but taken together they are all of this graph, right? They are all the edges. So that's what it means. The edge set of G can be partitioned in this way into some number of cycles if it could happen, right, that there's only one way to partition these. The example I gave yesterday was like a cycle itself, right? So the cycle on n vertices, C sub n, that's an example of an Eulerian graph. In fact, you can tell me immediately what's the degree of every vertex in a cycle like that. Well, it's 2, right? Each vertex is connected to 2 other vertices, right? The one previous and the one next. So that's like an extreme example where the graph simply is the Eulerian circuit, which is that cycle. This corollary also put a restriction on not just an Eulerian graph, but even a graph containing an Eulerian trail. Right, so this was different because, for instance, we had this example. Maybe I'll just quickly draw it. Again here, this house, right, on 5 vertices, we had this example where this is not Eulerian because it doesn't contain an Eulerian circuit, but this does contain an Eulerian trail. And to see the Eulerian trail, this is just, we can go around the house and then here. Right? That is a trail. It does not repeat an edge even once. So that is most certainly a trail. It is not a circuit because it ends at a different vertex than it began. So it's not a circuit, and it hits every edge in the graph. So this is an Eulerian trail. This corollary says that a graph can only contain an Eulerian trail if and only if there are at most 2 vertices of odd degree. And you'll notice about this graph, this vertex has degree 2, this vertex has degree 2, this vertex has degree 2, but this one has degree 3, and this one has degree 3. Having a single odd degree vertex means you can't be Eulerian, but having no more than 2 means you at least contain an Eulerian trail. Okay, but more than this, more than 2 vertices of odd degree, means that you can't even contain an Eulerian trail. So this is nearly a complete answer to what sort of graph structure is required for this to happen. Okay. All right. Now, I mentioned yesterday that the proof of this, I may walk you through maybe in, again, a future homework. So rather than, I think, go over it now, I might take you like step by step through it in a future homework. So I think that's what I'm going to do. So from now I'm going to move on. But this is a very satisfying answer for a question of what does it mean for a graph to be Eulerian, or what properties does this imply the graph has to have, right, in order to be Eulerian, and we get these nice equivalent conditions. So this is a massive restriction. Being Eulerian is a massive restriction. All of the vertices have to have even degree, which is quite the thing to ask, right? Okay. Now, the question is how to identify an Eulerian circuit in a graph if one exists. Obviously, you can't identify an Eulerian circuit if it doesn't exist, so we're not going to bother with that. But going to discuss one. There is another example we'll also talk about, again, in homework problems. But this is Hierholzer's algorithm for identifying Eulerian circuits. So, given an Eulerian graph G, of course, it makes no sense to talk about this problem for a graph that is not Eulerian, where an Eulerian circuit doesn't exist. So here we say at least this graph is Eulerian. And so I need to first identify a circuit, period. Okay. So identify a circuit in G and to call it, say, R1. Mark the edges of R1 and let I be equal to 1. So next step. If R sub I contains all edges of G, then stop. We have found the Eulerian circuit, right? We stop because since this R sub I would be an Eulerian circuit. Okay. But if it does not contain all the edges, then I identify a vertex in this R sub I that is incident with an edge that is currently unmarked, right? So if R sub I does not contain all edges of G, then let V sub I be a vertex on R sub I incident with an unmarked edge. We'll call this unmarked edge E sub I. Okay. Now, I want to build a circuit starting at this vertex and using this edge and then mark the edges of that circuit. So build a circuit, call it Q sub I, starting at vertex V sub I. Using this unmarked edge, or previously unmarked edge, E sub I, and then we mark the edges of Q sub I. Now, I want to create a new circuit, another circuit, that I create by patching this circuit Q sub I into R sub I at the vertex indicated. So create a new circuit, R sub I plus 1, we'll call it, by patching Q sub I into R sub I at vertex V sub I. In this case, increment I by 1 and go back to step 1. Or, I guess, rather step 2. Makes more sense here. Okay, so let's go over this one more time, and then I'm going to see an example of how this plays out. So, we start with an Eulerian graph, and before you get too worried, right, if it's Eulerian, then, well, you know that it is connected, among other things. So, you don't have to worry about like this process ending before you think it's going to, right? Or having issues because at this step, when you have this VI here, it's not incident with some other unmarked edge. Like there has to be a thing like this because it's connected. Okay, so we identify a circuit, mark it, mark the edges. If that circuit contains every edge in the graph, it's an Eulerian circuit, we can stop. If it doesn't contain every edge in the graph, then we pick a vertex that is incident with one of those edges, that it's not present in the circuit. We label that edge this E sub I or E sub 1 at the first step. And then we build a circuit Q sub I starting at this vertex using this edge, mark those edges, and then I patch this in. I patch this circuit into my old circuit, and that's how I get the iterative step here. Let's see how this works in a graph. Okay, so I'm going to show the following graph and the following process here. So let me zoom in. It's a little bit out of focus still. Hold on. There we go. Okay. So here's our graph. There's our labeled vertices. The circuit that I pick, for whatever reason, right, I pick a circuit here beginning at the vertex E, going E, G, H, J, back to E. This is the circuit that I pick. This is my R1. Okay. So then what I do is I notice, oh, well, there is a circuit Q1. So first of all, there are multiple vertices that I could pick for this next step, right? There's not a unique choice here. So let's say that I pick H. First, I ask myself the question, does this circuit contain all the edges of this graph? Clearly not, right? And so I pick any vertex in the circuit that is incident with an edge that's not marked here. So for instance, this H is incident with this edge going to D. It's not marked in this circuit. Okay. So then starting at H, I can build another circuit that goes H, D, C back to H. Okay, that's actually the shortest circuit, right? Link 3 that I can make here. Okay, there it is. So there it is. Okay. Here it is over here. Now the idea is I want to patch that circuit into the previous circuit at the vertex H. And literally that looks exactly like this. So that circuit that I built starting at H, ending at H, I patch it in right here. There it is. Right? So this is my R2. Now the question is, and you see here in bold, this is how this was patched in. Okay, so you refer to it as patching because in the picture it might look like you're just literally stapling this thing on here. But if we go back to how our circuit proceeded, it was EGHJE, so EGHJE. The way this goes is when you get to H, you take a detour via this circuit that you identified here, this Q1. So this is the detour that you take patched in at H. So you get to H and then blah. You have this detour and then it is bookended by what you were doing before, right? So EGH, you get to H, you do the circuit that you came up with here. That's your detour. And then now that you're back to H, you go JE. You finish the circuit R1 from before. Okay, so this is how we have built this circuit. Now we ask ourselves, does R2 contain every edge in this graph? No, it doesn't. So since it doesn't, that means that some vertex here must be incident with an edge that's not marked. Again, there's multiple choices here. C is incident with this edge going to A, it's incident with this edge going to E. E is incident with the edge going to I and going to C. D is incident with the edge going to B. H is incident with the edge going to I. There's multiple choices you can make here. Okay. So now what do? I might say, well, what can I choose? I could choose a circuit starting at D and going like D, B, A, C, E back to D. So basically this whole thing. Right? And just to maybe show with the pen. So that's an option. This is not the only option, but it is an option that I can do here. Okay, so I could do that and then patch that into this circuit. If I do that, so this Q2 that I've come up with is D, B, A, C, E, D. And so in the point of R2, when I get to D, I have this detour on my circuit to do first. So there. This is what it looks like. Again, we ask ourselves, does this actually contain all the edges of the graph? No, it doesn't. Pick a vertex that's incident with some edge not marked, H. But notice I can form the circuit H, I, E, F, H. Textbook does it as H, F, E, I, H. That's perfectly fine too. I can patch that in at H to get my final circuit, R4. Here it is. It contains every edge, never repeats an edge. Okay. So this is how the algorithm works. Try it for something simpler, right? Try it for the house that we did. You'll quickly see how this works for that because there's not a whole lot going on. But this is, for for the house, you can't find a circuit. You can find an Eulerian trail, though. See if this would help you in that regard. Again, there's so few vertices that it's hard to actually see what's going on here. Does the graph R have to be an Eulerian circuit? Yes. So this has to be an Eulerian graph in order to do this, because you would not be able to come up with a circuit that did this if it wasn't. So the problem, of course, of finding an Eulerian trail is less restrictive than an Eulerian circuit, because you don't have to start and stop at the same vertex. But this is an algorithm that will find an Eulerian circuit in an Eulerian graph. But yes, the graph has to actually be Eulerian, or this won't work, because there won't exist such a circuit. So you would not be able to find it. So that is that. Just for a second before I move on, the whole characterization of Eulerian graphs as having all their vertices have even degree is extremely nice, because to know whether or not a graph is Eulerian, all we have to do is check the degrees of the vertices, which is not so bad. And in fact, to answer the question definitively, all we need to know is that there doesn't exist a single vertex of odd degree. That's it. Once we know that, we know that it's not Eulerian. If we know that there does not exist an odd degree vertex, then we know it is Eulerian. So it totally pins the answering of this question to knowing all of the degrees of the vertices. That's it. So that's nice. For instance, if I gave you a degree matrix, right, for a graph, you would be able to tell me instantly whether or not the graph was Eulerian, because you're looking at all the degrees in the matrix, and you can just see, are there any odd numbers here, right? So that's nice. Okay. So naturally, this leads to a topic that might seem very related or relatable to what we're talking about, which is the notion of Hamiltonian paths in cycles. So Hamiltonian paths in cycles. You may have heard the word Hamiltonian before in a different context, maybe either from physics or mechanics, differential equations, solving exact differential equations, things like that, or finding an integral for a system of differential equations. But in this context, it's going to mean something different. And so a quick little side note on the naming here, why we call these Hamiltonian paths. So in 1859, the English game company Jacques and Son bought the rights to manufacture and market what's called the Icosian game. You might not have ever heard of it. Wasn't exactly super popular. But what was the point of the Icosian game? The game involved 20 pegs, numbered 1 through 20, and a game board with holes. Let me show you what the game board looked like. There it is. So there's what the Icosian game board looked like. Let's get a sharp picture. There's what it looks like. There's 20 of those holes. Okay. So notice this. The circular edge on the outside is just the edge of the board. That's actually not the play area. Any of these holes are the play area. That's where the pegs go. Okay, so what was the point of the Icosian game? So there's 20 pegs, numbered 1 through 20, and a game board with holes. So players were required to place the pegs in the holes in such a way that every pair of consecutive integers, along with the pair 1 and 20, were directly connected by one of the lines on the board. So it was connecting these peg holes. The pegs are numbered 1 to 20 in a way that when you have, say, the number 1 here, it needs to be connected to its, wherever you have number 1, it needs to be connected with consecutive integers all the way up to 20, and 20 needs to be also connected to or adjacent to 1. Okay, and you were to do this using these numbered pegs in a path in this way. So you were placing the pegs in these holes such that every pair of consecutive integers along with the pair 1 to 20 were directly connected by one of the lines on the board. There was another version of the game that had this exact same board design, except it was on the exterior of a D12 of a dodecahedron. And the idea was finding a round trip around the world, around the solid, around the D12, traveling only on the edges and touching each vertex once. You might notice if I bring the game board back that you'll notice how many vertices there are here, how many edges there are for each of these faces, how this shape can be formed into a dodecahedron, a D12. Okay. So that now traversing from a vertex to a vertex is traversing an edge of the dodecahedron on one of its faces, right? So neither of those games, neither of those versions were super popular. I think that version was called Voyage Around the World. I think this same company is the same company that makes Tiddlywinks and Chutes and Ladders and things like that. So they weren't total failures in terms of games they were trying to put out, but this one didn't do as well. But the inventor of this game was Hamilton, of course, a famous mathematician, famous for. So William Rowan Hamilton, he was very famous for a number of things. You might have heard of the quaternions, Hamiltonians, coming from physics. Like there's a lot too many things I could mention that Hamilton did. But among the other things he did was this graph theory sort of question, and so that is why he gets his name on this. You'll see how it is related to the Icosian game here in a second. So what is the definition I seek of a Hamiltonian path? So quick definition. If a path spans the vertices of a graph G, we'll call our path P. Spans the vertices, what does that mean? That means that the vertices that are present in P are all the vertices of G. So it just means that this is all the vertices of G. Okay. So if a path spans the vertices of graph G, P is said to be a Hamiltonian path of G. Any graph containing a Hamiltonian path is called traceable. So any path containing a any graph containing a Hamiltonian path is called traceable. That's a nice intuitive word to use for why that is the case. Consider why this would be called traceable. Maybe think about it. We're going to see some examples here. It'll make it clear. If a cycle C spans the vertices of a graph G, such a cycle is called a Hamiltonian cycle. And any graph containing a Hamiltonian cycle is called a Hamiltonian graph. Now, we might just say if G contains a Hamiltonian cycle, we would just say it is Hamiltonian, right? That's what we'd say. Okay. Now, of course, a Hamiltonian graph contains a Hamiltonian cycle. A cycle is a path, right? It's just a closed one. So a Hamiltonian cycle existing in graph G means that a Hamiltonian path exists in G, because in both cases these span the vertices. So any Hamiltonian graph is traceable, but obviously the converse is not true. So note, just from this definition, any Hamiltonian graph is traceable, but not every traceable graph is Hamiltonian. See if you can think of an example before I give you one here in a second. Okay. So the question is, so first of all, before we move on and talk about maybe some consequences or some examples of Hamiltonian graphs, let's think. So how is this related to the notion of an Eulerian graph? These definitions are very similar. It's just that instead of talking about trails and circuits, we're talking about paths and cycles. But of course, that's a big deal, because one of these conditions, being Eulerian, is referring to the edges, right? So it's really everything involved is referring only to the edges, so that we are trying not to repeat any edges. Repeating vertices is fine, right? But in the Hamiltonian case, you are focused on paths and cycles, which means you're focused on the vertices. You're not talking about spanning the edge set. We didn't really call it that when we were talking about an Eulerian graph, but that is the notion that we're talking about, spanning the edge set. So Eulerian graphs, and everything about Eulerian graphs, how we defined it, was talking about spanning the edge set, and we talked about circuits and trails. In the Hamiltonian case, we're talking about spanning the vertex set, and we are talking about paths and cycles, right, rather than trails and circuits. Okay, so that's one difference, and of course, that might not seem like much of a difference, but it's a big difference. So that's one thing right out of the gate. It is natural to ask the following question: what kind of restrictions does being Hamiltonian impose on a graph? We asked this question, of course, for Eulerian graphs, and our answer was this very nice theorem that I reminded you of at the beginning of the lecture, which is namely this, right? If G is Eulerian, every vertex has even degree. The edges can be partitioned into edge disjoint cycles. Even just talking about an Eulerian trail rather than an Eulerian circuit, um, even having an Eulerian trail was extremely restrictive in that you could have at most two vertices of odd degree if that was the case, right? So this is a big deal because this really, really nails down what an Eulerian graph could look like. The question is there an analogous theorem for Hamiltonian graphs? Can we similarly say, oh, it's Hamiltonian, therefore we know this about the degrees of the vertices, we know this about uh, we know this about how connected it has to be. For instance, talking about being K connected. Is it enough to just say that it's 4 connected? Is that good enough, right? There's all kinds of questions we could ask, and the answer is this is actually complicated. There's no simple, easy answers. There are some things that I am going to cover as restrictions here. There are some things that some restrictions that are placed on it, but trying to come up with something like this previous theorem on an Eulerian graph is extremely restrictive. Um, so so this is extremely restrictive because of how much it nails down the graph. There's not anything like that for Hamiltonian. Okay. And so, here is the fact. So here's some facts. There are Hamiltonian graphs with all even degrees. Here's one of them. The cycle on 10 vertices. The cycle on 10 vertices. What's the degree of every vertex? 2. It is Hamiltonian. The Hamiltonian cycle it contains is the one cycle itself. Remember that for a cycle, the way we get around this, you might say, wait, but a cycle repeats vertices, right? The end and beginning vertex are the same. But remember how we get around this, where we say, well, a cycle is really all of the vertices of the graph, and then we're including mentally that last edge that connects them. Okay, so really what's important is we've spanned all the vertex set, and it's a cycle because we take it together with that last edge. So no, there's no repeating vertices. Um, so this has all even degrees. There are also, maybe I'll just write this as a second fact. There are Hamiltonian graphs with all odd degrees. Well, the complete graph on 10 vertices is one such graph. What is the degree of any vertex in the complete graph on 10 vertices? And quickly, well, it's 9, right? They each have degree 9. So, because every vertex is connected to every other vertex. So, any vertex in case of 10 is degree 9, which is odd. But case of 10 is that is that is a Hamiltonian graph. It contains a Hamiltonian cycle. Think about what that cycle would be, or how you could get that cycle. You have a lot of edges, right? Got a lot of edges to span all those vertices, and so it's not too hard in the case of the complete graph. So there are Hamiltonian graphs with all odd degrees. Okay. Well, this is already telling you that Hamiltonian and Eulerian is these are very different animals in a way, because case of 10 is not Eulerian. We know that. It can't be. Right? You don't need to try to find an Eulerian circuit. You know it can't be because it has vertices of odd degree. So it can't be Eulerian, because Eulerian means all even degree. So no odd degrees are allowed. So for instance, here, case of 10 is an example of a Hamiltonian graph that is not Eulerian. Okay, of course there are simpler examples than that, but that's a good one. 3. This might mistakenly make you think that a Hamiltonian graph has to have like degree parity in this way. Either they're all odd or they're all even. Right? You're like, okay, so maybe that's the deal. The deal is that they either have to all be even or all be odd, but there can't be a mixture. Unfortunately, no, there can also be a mixture. So there are Hamiltonian graphs with a mixture of both even and odd. Let's just do an example of one of these. So let's take this, like the vertices of a regular octagon, put a vertex right here in the middle, and we connect all of these around this octagon, and then we connect each of these vertices with the one in the middle. Okay, so here's our graph. Let me really make clear where the vertices are, in case it's not. So that this has degree 3, this has degree 3. All these on the outside have degree 3. One in the middle has degree 1, 2, 3, 4, 5, 6, 7. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, degree 8. That's what I thought. Okay, so all of these have degree 3. All of these on the rim, and the one in the middle has degree 8. Okay. So, but this is Hamiltonian. So it's Hamiltonian, even though maybe I'll say we'll call this A and we'll call this one B. Degree A is 3, and the degree of B is 8. So this truly does have mixed degree parity. Okay. So Hamiltonian graphs can be whatever. What about non-Hamiltonian graphs? Well, non-Hamiltonian graphs can also have all even, all odd, or mixed. If you want to see an example of all even, here's one. Of course, this has all even degrees. It is Eulerian, of course, because of that. It is not Hamiltonian. I gave this as an example on like either the first or second day of lecture to show the distinction between paths and trails. So this is a great example to keep in your head for when you're thinking about the distinction between paths and trails, where there's absolutely no problem with a trail that traverses every vertex here and every edge. So none of the edges are repeated, so that's a trail. But with a path, you have an issue because you have to repeat this vertex, right? So that is where this is. We can't talk about a single cycle here. This is made up of two cycles, right? It's two cycle. It's literally two cycles stuck together at a vertex, right? Okay. Okay. So here's one, but all of the degrees are even here. So they're all 2 or 4, right? So everything has degree 2 except this one, which has degree 4. So all even, but this is not Hamiltonian. There's also all odd. So to see an example of all odd, the complete bipartite graph with partite sets of size 5 and 7. Everything has odd degree, but this is not Hamiltonian. If you want mixed, uh, the path on 9 vertices. All right. So, and you might say, why is the non-Hamiltonian? Well, why is the path on 9 vertices non-Hamiltonian? But you're forgetting. The requirement to be Hamiltonian is not to contain a Hamiltonian path. It's to contain a Hamiltonian cycle. Right? Containing a Hamiltonian cycle is the thing here. This does not. This doesn't contain a cycle period, right? In fact, this is a tree, right? So a piece of 9 is a tree, doesn't contain any cycles. So it can't contain a Hamiltonian cycle if it can't have any cycles. But this has mixed degree because the leaves have degree 1 and the rest of the vertices have degree 2. Okay. All right. So you might say, oh, okay, if I can't talk about degree parity, then what can I talk about as far as Hamiltonian graphs are concerned? Right? Okay, so if If degree parity doesn't work, and when we say doesn't work, i.e. to maybe fully describe Hamiltonian graphs, like that's what we mean to work here. In the same way that for Eulerian graphs, yeah, all the degrees of all the vertices have to be even, right? That's very restrictive. The question is there a similar thing that we can come up with for Hamiltonian graphs that that fully describe them in the same way, but we know it can't be degree parity because we've now seen too many examples of where it can just be whatever. The degree parity can be whatever in both Hamiltonian and non-Hamiltonian graphs. So if degree parity doesn't work, then what does? The answer of this is to say there are many, many results. I don't have enough time to go over them. There are years worth of results on this question. And we don't have enough time to something approaching exhaustively list all these things. The other answer, though, is that there's nothing as simple as it was in the case of Eulerian graphs. So we're not lucky enough that that's the case. Well, you might being lucky that a problem is harder. That's when you're a mathematician, right? Like you're lucky if the problem is harder. You're happy if the problem is harder in a way because that justifies your job, right? Like if the problem was easy, then you're opening yourself up to be less useful, right? So maybe you should always hope that the problem is as hard as possible, right? To justify further work. You don't want to be too hard. It can't be too hard enough that it's impossible. It can't be done. There's no point to employ you. But I guess you should want the problem to be just hard enough in that Goldilocks zone of just hard enough that not everyone can do it, but also not too hard that you can't do it, right? That's the sweet spot. So okay. So I can't exhaustively list like every single result here, but we will list a few. Again, none of them are going to be as far-reaching and as rigid and restrictive as the theorem for Eulerian graphs. Okay, so let's look at the first result. I think this was due to Dirac. Let G be a graph of order n greater than or equal to 3. So order at least 3. If the minimum degree of G is greater than or equal to n over 2, then G is Hamiltonian. So let's do a proof of this fact. This is very nice, of course. Notice this is not an if and only if statement. You could ask yourself, is the converse true? Ponder that. See if you can come up with an example that makes the converse false. But we do get, if we know the minimum degree is less than or equal to n over 2, then G is Hamiltonian. So, or sorry, greater than or equal to n over 2. I think I said less than. Okay, let G be a graph of order n greater than or equal to 3 with minimum degree greater than or equal to n over 2. Okay. We argue by contradiction. Suppose G is not Hamiltonian. Now, I can't answer you the question entirely of when do you know to do a proof by contradiction and when don't you know to do a proof by contradiction. In the strictest logical sense, if there exists a proof by contradiction, obviously there exists a direct proof. If there exists a direct proof, the proof by contradiction is obvious because you say, suppose not, then you prove the direct proof and you say, see, contradiction. So, so it's not a question of whether or not one will work. It's like when is this going to make your argumentation easier? Typically, the telltale markers of proof by contradiction is when negating the statement somehow gives you more to work with than assuming it was true. So negating the statement can sometimes give you something to work with where without using contradiction, it's not entirely clear where to even start. Here, what does supposing G is not Hamiltonian give us? If it's not Hamiltonian, then we can't construct a Hamiltonian cycle, right? It doesn't contain a Hamiltonian cycle. So if we think for a second about what this means, this is not being able to construct a Hamiltonian cycle in the graph means that the paths in the graph, if they start to be close to Hamiltonian, we know they have to fail somehow, and this is going to say something about, for instance, their lengths, right? So let's see where this goes. Let's suppose G is not Hamiltonian, and then let's let P be a path in G with maximum length. G is, of course, a finite simple graph. We have no problem having a path with maximal length. Say the vertices of the path, say its vertices are in order, so I'm labeling them in the order they occur, V1, V2, out to V sub P. Okay, so path length P has length P. Okay. Because P is of maximum length, we know that all of the neighbors of, say, V1 and VP are on P, right? Since P is max length, we know that all of the neighbors of V1 and VP, the endpoints, are on P. So all of the neighbors of its endpoints, V1 and VP, are on P. If they were not, you would extend an edge to one of them, call that path P prime, and that path would now be longer than P, which would contradict P being the maximum length path. So that is how we know that we can do this. Okay, I see a question in the chat about the previous non-Hamiltonian example, and yes, that's right. The middle vertex has to be met twice in that figure 8 type example, so that's why it's not one cycle. It's actually 2 cycles, and no, there's not a Hamiltonian cycle that spans the vertices of that graph. Okay, yeah, but P is max length, so all the neighbors of its endpoints are on P already, because if they were not, you could extend the path to include those neighbors, which would increase the length of the path, which you couldn't do if P is already at max length. Okay, so where have we used this assumption that minimum degree is greater than or equal to n over 2. That's where we're about to use it now. Since minimum degree of G is at least n over 2, each of V1 and Vp has at least n over 2 neighbors on P. So each of V1 and Vp has at least n over 2 neighbors on the path P. Okay. Now, the idea. We claim that there must exist some positive integer j, where j is between 1 and p minus 1, such that v sub j is in the neighborhood of v sub p, and v sub j plus 1 is in the neighborhood of v sub 1. But what about this? How do I prove this claim? So, proof of claim. Again, by contradiction, suppose this wasn't the case. So, suppose not. Then, for every neighbor v sub I of v sub p in the path P, or on P, I should say. And of course, how many of these are there? There's at least n over 2 such neighbors by this minimum degree estimate. Yes, Phantom. Delta of G is the minimum degree of a vertex in G. So it's the minimum amongst all degrees of all vertices. So suppose not, then every neighbor, there's at least n over 2 of them by this minimum degree estimate of VP on P. V sub I plus 1 is not a neighbor of V1. Now, if you're confused about why this implies that it's not a neighbor, well, if you couldn't do this, if basically there was a v sub I for which v sub I plus 1 was a neighbor of v sub 1, then that's saying that there is a j. In that case, it would be I. There is a j such that v sub j is a neighbor of vp, and v sub j plus 1 is a neighbor of is in the neighborhood of v1. That's like, this is what would have to happen if this idea is not true, right? It's that there doesn't exist a single index for which v sub j is a neighbor of v sub p, and v sub j plus 1 is a neighbor of v sub 1. So I can, if this is not going to be true, I can always assume that this next vertex, v sub I plus 1, is not a neighbor of v1. Okay. But what does that mean if it's not a neighbor of v1? What would this mean? This means that the degree of v1 is less than or equal to p minus 1 minus n over 2 But that, of course, is strictly less than n minus n over 2. The number of say the length of this path in question, right, is definitely less than the order of the graph itself. But n minus n over 2 is just n over 2. But this contradicts that the minimum degree of g is greater than or equal to n over 2, since this implies that the degree of this vertex v1 is strictly less than n over 2. Thus, the claim has to be true. Remind us, what is the claim? That there exists some j, some index j, such that v sub j is in the open neighborhood of v sub p, and v sub j plus 1 is in the open neighborhood of v sub 1. Okay. Thus, such a j exists. But then what does this mean? What does this look like? So I have a path, and without loss of generality, of course, a path on p vertices looks like this, up to there is some v sub j, and then the next in the path is v sub j plus 1, and then the next in the path is v sub j plus 2, and so on, all the way to v sub p minus 1, connected to v sub p. But this j is chosen so that j is adjacent, v sub j is adjacent to v sub p, and v sub j plus 1 is adjacent to v sub 1. It's in the open neighborhood. And so there is adjacency from v sub 1 to v sub j plus 1 here, and there's adjacency from v sub j to v sub p. So this is what the picture looks like. My path P is just this path indicated here, but there's these extra adjacencies that I haven't taken, right, connecting in this way. Well, what if we do something a little different here? Notice this turns our path into a cycle, if we're willing to see it. How? Let's see be the cycle that takes us from V1, V2, and so on, up to Vj. At the Vj mark, instead of going on along the path in the usual fashion, I'm going to go from Vj to Vp. And then I am going to go backwards along this path, Vp minus 1, Vp minus 2, and so on, all the way down to V sub j plus 1. But V sub j plus 1 is adjacent to V sub 1, so then back along this path. Now, yes, I know that I've repeated V sub 1 here. That's just to really say that I'm including this last edge. So this is a cycle, right? Because this is a path. I'm not repeating vertices here because it's the endpoint. Okay. We have assumed that G is not Hamiltonian. And so there must be at least one vertex of G that is not on P. Again, the reason for this is that if there was not such a vertex, then this cycle C would be a Hamiltonian cycle of G, which would make G Hamiltonian. Okay, so there has to be at least one vertex of G not on P. Also, since the minimum degree of G is greater than or equal to n over 2, G must be connected. I don't remember if I assigned this as homework, but this is an exercise in the textbook. I just can't remember if I actually assigned it as homework or not in your first homework set. I don't think I did. Maybe I did. I can't remember. But anyway, this is an exercise in the textbook. So G is connected. Therefore, there must be a vertex W not on P that is adjacent to a vertex on P. So say W that is adjacent to a vertex, say VI, on P. Think about this for a second. Why is this the case? So this is the case because if there was not a vertex that was not on P and adjacent to a vertex. So first of all, there has to be a vertex not on P or G is Hamiltonian because this cycle that I came up with would be a Hamiltonian cycle spanning the vertices of G. Okay, so there's got to be a vertex in G that's not here, that's not indicated here. Okay, then the claim is that there has to be some vertex, not indicated here, that is adjacent to some vertex on this path. And the reason for that is the connectivity. Because since there has to be at least one vertex here, if no vertex off of P in G was adjacent to this, it means that G is disconnected, right? We know the vertex has to exist, so then if not a single such vertex is adjacent to any vertex on our cycle or our path indicated here, then it would have to be disconnected. There would have to be no edges between those. They would have multiple connected components. Because its minimum degree is greater than or equal to n over 2, it has to be connected. Again, this is an exercise back in section 1. You can go have a look at. So, not only does a vertex off of P have to exist, one of these vertices that's off of P that has to exist in G is adjacent to some vertex here. And I've just labeled them. Say the vertex in question is W, and it's adjacent to a vertex V sub I on P. Okay, but then the path in G that begins with W, travels to V sub I, and then goes around the cycle, is now a longer path than our maximal path. Consider the path P prime that begins at W, goes to V sub I, then goes around cycle C. this is a path in G longer than P. But that's a problem. Why is that a problem? Why is it a problem if this path is longer than P? Because at the very beginning of the proof, we let P be a path with max length, but then we just found a longer path. So what is the only other thing that we assumed here that led us to this point, that we have a contradiction here? This is a contradiction. What is the key assumption we made that is the only thing that led to this? Well, we assumed that G is not Hamiltonian. The only way to fix this contradiction then is to say, oh, the problem all along was that G is simply Hamiltonian. It has to be. So this is the only way to alleviate this logical contradiction, is that it was actually Hamiltonian all along. And that's that. That's the proof. Okay. This, let's go back. While, of course, this isn't a complete characterization, it is still very nice. Here's the question. How good is that lower bound? How good is that lower bound? So first, some facts. 1, the lower bound in this theorem is the best possible. To see this, take G to be the complete bipartite graph with partite sets of size R and R plus 1. This is not Hamiltonian. I'm not going to prove that for you. That will be done also in a future homework or maybe an exam. It's not Hamiltonian. And the degree of G is, or the minimum degree of G is strictly between the following. It's strictly between the vertex set, the size of the vertex set of G over 2, and the size of the vertex set over 2 minus 1. So this provides an example. And if you're even slightly smaller than n over 2, then you can have this example here of not Hamiltonian. So this is as good as you can do. Second, as I said, this does not characterize the Hamiltonian graphs. So as I keep beating you over the head with, Unlike the Eulerian case, where you had a complete characterization, an if and only if statement, Eulerian graph has to have all even degrees of all the vertices. Um, for a Hamiltonian graph, we know that's not the case, but even this bound itself is a little silly when you look at some of the possibilities here, right? So, what about the cycles? What's the degree of any vertex in a cycle? Will someone tell me? Well, 2. And this is true for all I. So, hmm, that's a really small minimum degree, right? So, i.e., there are lots of Hamiltonian graphs with very small minimum and even maximum degree. In fact, the max degree of this cycle is also 2, right? So um, all the degrees are 2, right? So that's the thing as for why this theorem is not super useful in the sense that you think you might be able to characterize. Ah, yes, I know exactly what the thing is now. Um, this imagine a big cycle. All these degrees are just 2. It's Hamiltonian. But if you were looking at this theorem, you would need that its minimum degree is greater than or equal to n over 2, and n could be very huge. So it's like, that's it is not a complete characterization of Hamiltonian graphs, that is to say. So before, when I was goading you into coming up with an example on your own that shows that this if and only if statement, this is not a complete characterization. This is kind of what I was leading towards. So thinking of like the cycles, for instance. There's other examples as well. Okay. So this is these are both important things to keep in mind, and of course we're going to see, because of how much time we spend on some of these results, we're going to see that you will develop an intuition that Hamiltonian is a more complicated beast when it comes to describing a Hamiltonian graph, because we're going to have so many results that require very precise statements to get a conclusion that the graph in question is Hamiltonian. So that's how, like, after seeing these over and over again, you won't think to yourself, "Oh yeah, Hamiltonian. That's it. That's an easy. I have an easy fix or understanding for those things." So actually, that previous theorem of Dirac is actually a corollary of the following. So there's a theorem that It's a little bit more general and contains our previous theorem as a special case. Let G be a graph of order n greater than or equal to 3 if the degree of x plus the degree of y is greater than or equal to n for all pairs of non-adjacent vertices x and y, then G is Hamiltonian. Think about how this is related to saying the min degree is greater than or equal to n over 2. So think about how this statement is related to this statement, and how actually this is a special case of that. This is a stronger thing. Okay. Question in chat, will the third homework contain topics around Eulerian graphs? Yes, third homework will contain Eulerian stuff, Hamiltonian stuff, a little bit more depending on what I finish up through tomorrow. So basically your third homework will contain all of the stuff that I finish by the end of lecture tomorrow. Okay. So the proof of this is similar to the Dirac theorem. In fact, this is also a homework exercise, but I probably won't assign this one. But maybe I should, to kind of force you to read through that previous theorem again, because it's a useful example of kind of a typical proof by contradiction in graph theory. So let's discuss another thing that allows me to talk about Hamiltonicity. So let's state the following. I need to make a definition first. So a set of vertices in a graph is said to be independent. Said to be an independent set of vertices if they are pairwise non-adjacent. The independence number of a graph denoted by Greek letter alpha of G is defined to be the largest size of an independent set of vertices from G. The largest cardinality here. Okay. So let's do a quick example. So There's some quick examples. So let's draw this thing. There we go. And we'll label these going clockwise here, A, B, C, D, E. Call this graph G1. G2 is the cycle on 6 vertices. Okay, so there's 2 graphs. The question is, find some independent sets, right? So find some sets that are independent. Well, independent sets of size 1 are not super interesting. So independent set of size 2 in G1. Let's see. So if A is in the set, then B, C, D, or E can't be in the set. Oh, okay. If B is in the set, then A, E, D, and C can't be in the set. Oh. Same thing for E and D, or rather for E. So if E is in the set, then none of the other vertices can be in the set because it's adjacent to everything. Okay. D is not adjacent to C, but it's adjacent to everything else. C is not adjacent to D, but it's adjacent to anything else. So the largest possible independent set is the set containing the vertices C and D. Those are the only 2 vertices that are not adjacent. And of course, any larger set is going to contain something that one of these are adjacent to, so that's it. So here, alpha of G1 is 2. That's the largest possible independent set. Here, in G2, if I've labeled these, again, clockwise, A, B, C, D, E, F, well, A can be in the set, but then B and F can't. So then C is fine, but then B and D can't. But then E is fine. So like ACE is fine. Right? ACE is fine. Also, for the same reason, BDF is fine. So there's 2 distinct sets of size 3. Can I have an independent set of size 4 in G2? Well, no, because if A is in the set, for instance, neither B or F can be in. Okay, so then that leaves me C, D, and E. But if D is in the set, then C and E can't be in it. So I would just have a set of A and D. That'd be it. So C can be in the set, but then D and B, I've already covered B. So yeah, I'm left with A, C, and E. That's it. So this is the largest size. Both of these are the largest size they can be. So alpha of G2 is 3. So G1 has an independence number of 2, and G2 has an independence number of 3. Okay. So, what do I want to do here? Well, I'm going to basically. Do I need to introduce any more notation here? No, I can just go ahead and state this in terms of the independence numbers. So here's the following theorem. This is due to Erdős and Schwatal. that relates this independence number to connectivity of a graph. So let G, and also Hamiltonicity. So let G be a connected graph of order n greater than or equal to 3 with vertex connectivity kappa of G Remember how this was defined back in section 1. And independence number alpha of G. If this connectivity kappa of G is greater than or equal to the independence number alpha of G, then G is Hamiltonian. Now, I do not have time right now to prove this. This is on pages 63 and 64 in the textbook. I may talk briefly about the idea for the proof at the beginning of tomorrow's lecture, but this is all I wanted to say for now. So this inequality is sharp, just like in the Dirac theorem. So just like the Dirac theorem, this inequality is sharp. Okay, i.e., graphs that satisfy that their connectivity is greater than or equal to the independence number minus 1 are not necessarily Hamiltonian. Can you find an example? Hint. I'll give you a hint here. The same example in the Dirac theorem works. When I say in the Dirac theorem, I mean the same example that showed that the inequality for the Dirac theorem was sharp is also the same example that shows that this inequality is sharp. So it's the complete bipartite graphs of size difference 1 of the partite sets. So it's think about why that is. I wanted to say one more thing. This will be the last thing I say, just to get it out, because I included it in the description for today's video, so it's nice if I don't have to edit the description, take it out, although I don't have a problem doing that. This is just a nice place to stop here. So next, we have our first example of what are called forbidden subgraph results. So what this means is results about a graph based on it not containing certain forbidden subgraphs as induced subgraphs. That's what it is that's going on. So let me explain this entirely. This is where the difference between a subgraph and an induced subgraph is extremely important, and it won't make sense if you don't understand that distinction. You won't understand why these graphs that seem like they have forbidden subgraphs in them don't, according to us. So that's why it's very important to understand the difference between induced subgraphs here. So given graphs G and H, if G, I should write G, if G does not contain H as an induced subgraph, I'll remind you all next time when we go over this what induced subgraph means versus subgraph. Then we say that G is H-free. If S is a collection of graphs, a set of graphs, if you will, and G does not contain any of the graphs in S as an induced subgraph, then we say G is S-free, where S is that collection. Now, I'm going to list some special graphs. And I'm going to give them names. So here is one that we know already has a name. This is the complete bipartite graph of partite set size 1 and 3. This is otherwise known as the claw. There is this graph, which for now I'm just going to call Z1. And there is this graph, which I'm going to call N for now. This graph is going to come up an awful lot, so much so that we're going to actually modify this to, we're just going to directly say that G is claw free if it doesn't have the claw in it. But these are the special graph names we need, and or that we're going to be using immediately. But the following theorem is our first example of what we call a forbidden subgraph theorem, which states that if G is a two-connected K13 and Z1 free graph, then G is Hamiltonian. Remember, two-connected means its connectivity is at least 2. Okay, so G is two-connected and claw-free and Z1 free. Then G is Hamiltonian. So I get that G is Hamiltonian. First, we say it's two connected, but the Hamiltonicity comes from us saying that G doesn't contain this graph nor this graph as an induced subgraph. This is, you see now why this is called forbidden subgraph result, because it's saying that we get some property of G, in this case Hamiltonicity, comes from forbidding these graphs to show up as subgraphs of G, induced subgraphs of G. Okay. So that is what we mean by a forbidden subgraph result. Okay, that we learn some further property of the graph once we know it does not contain certain naughty subgraphs. Okay. So anyway, we will continue on with this. This is the first place we'll start tomorrow. We have a lot of stuff to say about these forbidden subgraph problems, and I have plenty of examples to do to show you why. You're going to be looking at some of these examples, and you're going to say, wait, there's the claw. I see the claw in this. I see the claw in the picture. So in fact, might as well just go ahead and do this. Let me give you a picture here somewhere. Yeah, here. Here's a graph. This graph is claw-free. It's three connected and claw-free, and it's non-Hamiltonian. Okay? Now, I say this is claw-free, but you look at this and you say, wait, there's the claw. Right here. Huh? There's the claw. Doesn't that look like the claw right there? Well, no. But to understand that, you have to go back to the definition of induced subgraph versus just subgraph. Okay. So that is what we are going to be doing, and that's the direction we're going in with this stuff for the next couple lectures. So yes, there's a question: will forbidden subgraph results be in the next lecture? Absolutely, we're going to be talking plenty about them in tomorrow's lecture and in subsequent lectures. For the remainder of the graph theory stuff, this is going to be a tool in our toolbox. So anyway, that is all for today. So I'm gonna stop after tomorrow's slightly extended lecture. We'll be back to a normal lecture schedule, hopefully for the remainder of the course, so that all these lectures will be an hour and 20 minutes long, since we've had to make up for 2 missing lecture days. And so instead of having, by the end of tomorrow, you would normally have had 10 lectures, you will have had 8, but those 8 lectures will contain 10 lectures worth. 10 1-hour and 20-minute lectures worth of material. So you're not getting shortchanged. You're getting it all. Anyway, that is that. Your homework 2 is due tomorrow at night. So if you have questions, come tomorrow. You can ask me after lecture. So I'll post a separate stream for that and let you guys know. But anyway, yep, I will see you tomorrow. As always, let me know if you have questions about anything.